It turns out for our work on this test, I've already laid a good foundation with our work from functions when we were doing the improper integrals. So if we compare rates of growth in a ratio of two functions inside a limit as inputs head toward infinity, the result of that limit, if you'll remember, will tell us which function is growing faster than the other and which is growing slower, or for large input values, which is bigger and which is smaller in the plane. I'm not going to rehash all the information that we went through with the functions. You're welcome to look back in your notes on limits of integration when we talked about, sometimes it helps us just to compare what one function is doing as far as convergence or divergence, a known function with some unknown function. And so we did that when we couldn't actually figure out whether the unknown function was converging or diverging. And there were three results when we did that. When we put our two functions in a ratio, always making sure that we know about convergence or divergence on the denominator function. We know about convergence or divergence for g of x. And so knowing that, depending on which of these three results that we got out of that ratio inside that limit, it could tell us what was happening to convergence and divergence on our unknown function. If we got a real number value between 0 and positive infinity, it told us that those functions were growing at the same rate. So if g of x was converging, that told us by comparison that f of x was converging as well. If g of x was diverging, f of x was behaving the same way. These other two results were a little more ambiguous. Sometimes they were helpful, sometimes they weren't. So we had to be careful that we knew what g of x was doing. If we put those functions in a ratio and we found that the result of that limit as x approached infinity was 0, then it clearly told us the function on the bottom was growing at a much higher rate than the function on top in order for that limit to go to 0. And in order for the limit to go to infinity, it told us the function on top was growing faster than the function on bottom. So here, if we knew g of x converged, it was helpful, so f of x, which is smaller, must also converge. Okay, it did not help us, however, for g of x to diverge. There's no help in knowing what f of x was doing. F of x is smaller than g of x in this case. It could go ahead and diverge, or it could converge. So that wasn't a helpful result when the bottom function diverged, but it is a helpful result if the bottom function converges. And in the same vein, here, this was only helpful if g of x diverged, then that told us f of x, which is bigger in this case, must also diverge. However, it wasn't a helpful result if g of x converged. It was no help on f of x because to know that my function was bigger than a convergent function didn't tell me anything about it. F of x could go ahead and converge, or it could go ahead and diverge. So getting these results were helpful, these two most especially, but they all hinged on what our known function was doing. And only if it was doing one thing in particular was it a helpful result. And we're going to take all that work from functions and we're going to carry it forward to our series, to the sums of these series. And this is going to actually be called the limit comparison test. So let's say we know what b sub n does. We know b sub n is a known series like a p series or a geometric series, and we know up front whether it converges or diverges. We can put these series, these nth terms of these series in a limit, and we can compare their behavior to some known series, b sub n, with some unknown series, a sub n. So here, we're going to say that we know the behavior of b sub n. We know whether B sub n converges or diverges. The problem that they're giving us, the one that we're supposed to find out whether it converges or diverges, we're going to call A sub n. So in the vein of our functions, this would be like g of x, and this would be like f of x. Okay? We're going to know up front what B sub n does. We're not going to know up front what A sub n does. But we're going to plug them both in a limit, and we're going to see if the results of that limit are going to help us. So make sure it's clear in your notes that our known series is B sub n, and the known series always winds up in the denominator. Okay, that's where we're going to put B sub n. Our unknown series that we're asked to find the convergence or divergence of, we're going to call A sub n, and we will always put it in the numerator. One caveat for the limit comparison test is it works on positive series only. A sub n and B sub n both must be positive series. In other words, we're only getting positive values out. Our sum, A sub 1, A sub 2, A sub 3, A sub 4, is only made up of positive terms. All right? So if we put this ratio of our unknown to our known, unknown to known, inside of this limit, and now we're working in n because we're working with nth terms of series, and we get some real number value out of it. C is some real number value, not 0. Then that tells us, just like it did for our functions, that they both exhibit the same behavior as far as convergence or divergence. And this is super helpful because we're already going to know what B sub n does. So we hope when we put these two series inside this limit, we hope we get some real number value. Because it takes all the guesswork out of which is bigger and which is smaller, and is this a good result? Yes, it's a good result, because this tells us they behave the same way for large input values. That is a super useful result, because we're going to know whether B sub n converges or diverges. The other two results, as with our functions, we're going to have to take a little more information into consideration. Again, up front, we're dealing with positive series only. A sub n is a positive series, B sub n is a positive series for all n values. We're going to know what B sub n does. Okay? We're going to know what B sub n does. We put them in a ratio of unknown over known. If we get 0 as a result, that tells us A sub n is smaller than B sub n for large input values. That's helpful. That's helpful only if B sub n converges. Because if B sub n converges, every other series smaller than B sub n must also converge. So it tells us A sub n converges if B sub n converges. Okay, if a larger series is convergent, any smaller series must also be convergent. So that is a good result only if B sub n converges. Okay? And lastly, positive series only again. If we put them in a ratio, and we put the unknown series over the known series, and we get infinity as a result, that tells us that A sub n is bigger than B sub n. And any series that is bigger than a divergent series must also diverge. So this is a good result if and only if B sub n diverges. All right? So we're going to get the same results, the same kind of idea that we did when we worked with our functions, but now we're working with series, and we're talking about series convergence or divergence. The power, once again, is that we're going to know what the series on the bottom does. The big question is, are the results of equal 0 and equal infinity as helpful as we might believe they are? And there's only one case where either one of them is helpful. So let's put that in our notes. Some things we have to consider when using the limit comparison test. if B sub n diverges, this result tells us nothing. Knowing that our unknown series is smaller than a divergent series isn't helping us. You have to pay attention to the convergence and divergence of B sub n. That's like telling us, okay, here is a function that is behaving kind of sort of like B sub n. Let's call it g of x in your notes. And this limit tells us a sub n is down here somewhere. It's acting like this function, f of x. To know that B sub n diverges, and to know that a sub n is smaller than B sub n is not helpful. It tells me nothing. All right? So getting a result of 0 out of that limit is only helpful if your denominator converges, because that says your unknown series is smaller than a convergent series. That's helpful information. In the same way, if we get infinity out of that limit, and our known series in the denominator converges, this is not a useful result. This tells us that our unknown series is bigger than some convergent series. It's just the opposite of what we saw a while ago. We'll call this f of x, and a sub n is acting like that. We'll call this g of x, and b sub n is acting like that. To know that b sub n converges, and that a sub n is bigger than some convergent series is not helpful. It tells us nothing about our unknown series. All right, so make sure you're very clear on that. If we get any number besides 0 and infinity, then a sub n does what b sub n does. If we get 0 or infinity, it's only helpful if we know that a sub n is smaller than a convergent, or that a sub n is bigger than a divergent. That's the only helpful. All right, tips on finding a useful B sub n. You're going to have questions like this where they're going to give you a series. The unknown that they're asking you to prove convergence or divergence for, you're going to call a sub n. That's your unknown. You want to prove whether it is convergent or divergent. You are going to have to come up with a B sub n to compare it to inside the limit. Well, the biggest clue for finding B sub n is to determine how a sub n behaves for large n. This is going to help you most of the time. I'll be honest, it's not going to help you 100% of the time, but it's going to help you most of the time. It will help you find a B sub n to compare your unknown to. Now, there are some things we're going to have to do. This is a process. For large n, the plus 1 in the numerator is not really doing anything. The denominator is n squared plus 2n plus 1. For large n, that's not really doing anything. So for large n, that's how a sub n is acting. Now, I can have a constant, right, times an nth term, and it's not going to affect convergence or divergence. So really, there is a good choice for B sub n. So here's what I'm going to do. You're going to have to show the AP reader your choice for B sub n. Remember, that doesn't have to be there. It's assumed to be there if it's not. It's not enough to say, okay, here's my B sub n. You have to run a good test or identify B sub n and state up front that you know what B sub n does. B sub n diverges because it's the harmonic series. That work's got to be done up front before you put them in that limit. Here's the end of this video. Look for the next one. We'll finish this example.